we have determined the number of KCL equations. Now, similarly, we have to determine the number of KVL equations that we can write for a circuit with n nodes and b branches. Okay. Now, this is slightly more complicated than counting the number of Kirchhoff's current law equations, but of course, still can be done. I will still consider the same circuit. Okay. One, two, three, four nodes and 1, 2, 3, 4, 5, 6, 7, 8 branches. Okay. So, now how do we count the number of KVL equations? First of all, we write KVL equation around loops. Okay. So, there is one KVL equation for every loop. Okay. And we have to find the number of independent loops. By independent loops, I mean, for instance, this branches 1 and 2 form a loop, branches 1, 6, 3 form a loop, branches 2, 6, 3 also form a loop. There are 3 loops, but it turns out there are only 2 independent loops. Okay. So, we can take either this loop and that loop or any 2 of them. Okay. Only 2 of them will be independent. So, how do we form independent loops? To discuss this efficiently without rewriting the circuit every time, I will introduce the concept of the graph of a circuit. The graph of a circuit is nothing but basically the same topology, the same nodes and branches, but we are not worried about what the branches contain, what elements there are. Okay. So, these are used for discussing general properties of circuits. So, we do not worry about what elements there are, we simply denote each of them by a line. Okay. So, the graph of this would be the same number of nodes. Okay. We have the 4 nodes and 8 branches. Okay. Graphs are widely used for analyzing general properties of networks. Okay, and there is a lot of theory behind it, but for us basically it is a simple depiction of the circuit. Okay. So, that is all we are going to use that for, and our goal right now is to find the number of independent loops in this graph. Okay. To do that, let me redraw the graph over here. Okay. So, to count the number of independent loops, what we do is first form a what is known as a tree. Okay. Now, what is a tree? Tree is a set of branches, which is basically a subset of all the branches. Subset of B branches of the circuit, which traverse all the nodes. Okay. So, all nodes should have at least one branch connected to it. But without forming a loop. Okay. So, this should be clear if I show an example. There can be many trees, okay. There are many possibilities, but you can start from any of them. So, let me show you one example of a tree. So, these are the 4 nodes, and I will take branches 1, 6 and 7. Okay. So, 1, 6, 7. So, clearly all 4 nodes have at least one branch, and there is no loop formed yet. Of course, this is not the only tree that is possible. There are so many others. You can just take this graph and then form them yourselves. I will show you just one other example. So, again I can take these branches, okay, these 3 branches, and there will be branches 6, 7 and 3, and again we have a tree and all nodes are connected to at least one branch, but there is no loop. Okay. So, this is also a tree, and you can form many others. Now, one thing you notice is that both of these trees, right, they have 3 branches. Okay. And you can sit and make any number of trees you can from this circuit, and you will find that all of them will have 3 branches. Now, is this a coincidence? Of course not. If you have n nodes, right, you start from one node, you go to the next one, you order the nodes in any which way you want. I have in this case shown 1, 2, 3, 4, but you could also have done 1, 2, 3, 4, etc. You take any ordering of the nodes, then you connect branches from node 1 to node 2, node 2 to node 3 and so on. So, clearly in going from node 1 to node n, by connecting a branch between every successive pair of nodes, you will have n minus 1 branches. So, if you have n nodes, the tree for the circuit will contain n minus 1 branches. Okay. So, there will be n minus 1 branches in an n node circuit. Okay. So, remember we are starting off with a circuit with B branches, and out of that we will take n minus 1 branches, okay, to form the tree. So, now what next? So, it must be pretty obvious what is coming next. Now, if I have a tree, what do I have? I have branches connecting every node of the circuit, and there is no loop yet. Now, if I add any more branch, that is, for instance, here I have taken branches 1, 6 and 7. So, what I have left out are, I will show them with dashed lines. Okay. I had left out 2, 3, 4, 5 and 8. It is pretty obvious that to a tree, if you add any of the remaining branches, you will form a loop. Okay. So, if I add branch 2, there will be a loop here. If I add branch 3, there will be a loop over there, and if I add branch 8, there will be a loop formed by branches 6, 7 and 8. Okay. So, once you have a tree, you add any branch to it, you will form a loop. Okay. So, now it is very easy to count the number of loops. So, we have a circuit with n nodes and B branches, and a circuit with n nodes will have n minus 1 branches in the tree. Now, out of B branches, if you take out n minus 1, we will have B minus n plus 1 remaining branches, which is also called the co-tree. Okay. Now, introducing each of these b minus n plus 1 branches to the tree will form a new loop. Okay. So, what you do is, you first form a tree and then you take these branches one by one and add them. That is, you take one of these branches, you form one loop, and you remove that, you take another branch, you form another loop, and so on. Okay. So, in our particular example, we will start with the, let us say, this particular tree. Okay. So, we had, let me put this down, we had 4 nodes and 8 branches. So, we have 3 branches in the tree and then 5 remaining branches. So, we will have 5 independent loops, that is, we have b minus 1 independent loops and consequently b minus 1 independent Kirchhoff's voltage law equations. Okay. So, just to illustrate this, I will show the loops. So, to this I add branch number 1, I form a loop, branch number 2, I form another loop, branch number 4, I form another loop, branch number 5, another loop, and branch number 8, another loop. Okay. So, there are 5 loops and I can have b minus n plus 1 Kirchhoff's voltage law equations. Okay. So, in an n node circuit we have n minus 1 KCL equations, and in an n node B branch circuit we have b minus n plus 1 KVL equations. Okay. So, earlier we said that we have to solve for 2B variables. Now, let us see how we get the 2B equations. Where do we get them from? First of all, we have n minus 1 KCL equations. So, this is for an n node B branch circuit. So, n minus 1 KCL equations, b minus n plus 1 KVL equations, and these two together will give us B equations. And also we have B branches. So, each branch will have its current voltage relationship. So, we have B IV relationships which give you B more equations. So, together we have 2B equations, and by solving these we can solve for 2B variables. And what are the 2B variables? B currents and B voltages in each of the B branches. Okay. So, this is how we set up the equations and solve for every variable in the circuit. Now, what we will do is we will look at a few methods of circuit analysis. Now, of course, it is not always that you use the systematic way of writing down all the equations and solving for every variable. We will also look at certain ad hoc methods that we use, and then we will go on to systematic methods which you have to use when you have somewhat complicated circuits, especially circuits with multiple sources. It turns out that when you have a single source, there are many simplifying techniques that you can use, but when you have multiple sources, you have to be a little more systematic. Okay.